In this video, we'll continue to explore some basic concepts from graph theory. So to begin with, we have some additional vocabulary terms. Okay, in the past video, we talked about vertices and edges of graphs. Okay, so let's begin with the degree of a vertex. This is the number of edges that intersect that vertex. So we have a number of examples here on the right. We have one, this vertex has degree 2 because there are 2 edges intersecting that vertex. We have a degree 4, so if you just focus on the vertex and see how many little lines are coming out of it, that tells you the degree. And then we also have one that's degree 6. There are 6 edges coming out of that vertex. Vertices can either be even or odd. Okay, even ones have an even number of edges intersecting, and odd ones have an odd number of edges intersecting. Okay, so here's some other examples of odd ones. Degree 1, degree 3 is 3 edges, degree 5, 5 edges. When we're counting the degree of a loop, we consider a loop to be 2 edges intersecting a vertex. All right, so even though a loop is a single edge, for the purposes of counting the degree, we say, okay, that's intersected the vertex twice. Okay. Adjacent vertices are vertices that have at least one edge connecting them. So they may not actually be anywhere physically near each other on the graph. They could be totally opposite ends, but as long as there is an edge directly connecting them, they would be considered adjacent. So in this graph on the right, A and E would be adjacent vertices because there's an edge that goes from A to E. All right, a path is a sequence of adjacent vertices and the edges connecting them that uses no edge more than once. So here's an example. Okay, and this is path B, C, E, F. And we label paths by listing the vertices and putting commas between them, and this shows the order that we're sort of walking along that path. Okay, so that's a path that starts at B, goes to C, goes to E, and goes to F. And we'd have to make sure that there are edges between those vertices to make that happen. Now we can use a vertex more than once in a path. That's okay. So if I did a different one here, okay, let's say that my path started at C, and I went to B, and then A, and then E, and then C, and then D. Okay, that's okay. That's a path. It crosses through C twice, but I haven't repeated any edges. All right, a circuit is a path that begins and ends at the same vertex. Okay, so circuit, circuitous, you've heard those words before. Okay, so this kind of makes sense in context. So here's a circuit A, B, C, E, A. Okay, starts at A and then goes around in that order and ends at A. Okay, some true or false. Every loop is a path. Right? Every path is a loop, every path is a circuit, and every circuit is a path. Right, so you may want to pause and think these through on your own, see if you can guess, and then we'll go over these. All right, every loop is a path. That is true. Okay, you could make a case for false on this one as well. I think all of the other ones are definitely true or false. But if you look at the definition of a path, okay, it's a sequence of adjacent vertices and the edges connecting them that uses no edge more than once. So if you want to say that technically a loop isn't a sequence of adjacent vertices, that it's just a single vertex, all right, if you want to say that, then you would say, okay, no, a loop is not a path. But if you want to consider this as kind of the one weird case where we only have one vertex, and if you want to notice that the important thing is that we're not crossing edges more than once, Okay, so if this is like a, A, then we're just going from A to A and going along one single edge. And then that would fit the definition of a path. Every path is a loop. Well, that's definitely false. We've already looked at many examples, well, not many, at least 2 or 3 examples of paths that were not loops. They did contain more than one edge. Every path is a circuit. That is also false. Right, circuits begin and end at the same place, and paths don't have to. You can just start somewhere and kind of meander along and end up at a different location. Every circuit is a path. That is true. Okay, so circuits are specific types of paths that just happen to end up at the same destination as where they began. Connected graphs are those where there's at least one path between any 2 vertices. All right, so if I looked at any of these examples on the right, I will pick out this middle one. If I pick any 2 vertices on this graph, there should be a path to get from one vertex to the other. So if I looked at vertex B and E, okay, I can kind of walk along this right side of the graph through C and D and get to E. Now that would have to be true not just for a single pair of vertices, but it would have to be true for every pair of 2 vertices. So I'd also have to check A and D, see if there's a path to get to those. And A and C, A and F, B and F, B and D, every possible combination of 2 vertices. So that could be kind of time consuming. There is a quicker way to figure this out. Basically, if you picture these graphs as maybe made of string and knots, if you can grab onto this graph at a certain point and kind of pick it up off the paper all in one piece, then that would be a connected graph. Okay. Now look at the 3 along the bottom here. Clearly that's not the case. So if I tried to pick up this graph, okay, I can start picking up one of the 2 pieces to it, but I can't get both all in one try. All right, so disconnected graphs are those where the graph is not connected and you can kind of see multiple pieces to the graph. Sometimes that piece is just a single vertex, and other times the pieces are vertices and some edges. A bridge on a connected graph is an edge that, if removed, makes the graph disconnected. So if the graph's already disconnected, then we don't talk about bridges. We only talk about this in the context of a connected graph. So here's this edge BE, and picture erasing that. Okay, if that one's gone, then the graph is disconnected. I'd have this square ABCD and this little triangle EFG, and no way to get between the 2 pieces of the graph. And notice if I pick out a pair of vertices like C and F, then there would no longer be a path between C and F, so that does not fit the definition of connected. This graph on the right, CD is a bridge. If I take that out, then there's no way to get from B to D, for example. And then finally, the third picture here has 2 bridges. Okay, if I take out AC, then A is disconnected from the graph. And if I take out CE, then vertex E is disconnected. Okay, so if you're having trouble seeing these, maybe try tracing these on your own or drawing these out, and then actually physically erase one of those bridges and see if you can tell that the graph is then disconnected. Okay, let's practice with all of the vocabulary that we've learned so far. List the odd vertices. Okay, so let's go through, and we need to find the degree of all of the vertices, and then we'll decide if they're odd or even. So vertex T, okay, that has degree 2. There are 2 edges coming out of that. Vertex U is also degree 2. V is degree 3. There are 3 edges. Y is degree 4. Z is degree 1. X is degree 3. And W is degree 3. Remember that for loops, In the context of degrees, we're counting that as 2 edges, entering W. Okay, so the odd vertices would be the ones with odd degree, so that would be V, W, X, and Z. Okay, the even vertices would be the others, so we've got T, U, and Y. All right, which vertex has a loop? Well, that's W. All right, are there any bridges? So are there any edges here that you could erase or take out, and then the graph would be disconnected? Okay, I see 2 bridges. All right, if I take out WY, then I have this little loop at W that's disconnected from the rest of the graph. And I also see YZ. Okay, if I take out that, then Z is disconnected from this entire rest of the graph. Right. Another common answer, some people say, let me write that one down, YZ. Some people say that this loop is a bridge. Okay, but notice if you do erase the loop, we're just erasing the loop and not the vertex W that goes with that. And that's okay. You can erase the loop and still have the rest of the graph be connected. All right, identify at least one circuit. Many answers here. What we need is a path that begins and ends at the same vertex. So we can't use any edges more than once. That's the definition of paths. But we can repeat vertices. Okay, so up to you, but let's do, I'll do this one here. Okay, so X, we started X, and then Y, and then V, and then back to X. That's a circuit. Okay, so that concludes this first section. It's an introduction to the basic concepts of graph theory. A lot of vocabulary in this section, so go back and review your notes and review the vocabulary. Try some of these concepts out, try some extra practice problems, and make sure you're getting the hang of all of these different terms before we go on to the next section.